In this video we're going to look at a particles question. Pause the video now and try all parts of this question. So part A says, why do the tubes of a LINAC, a linear accelerator, become longer down its length? Now you probably wouldn't get this on AQA because we don't really talk about linear accelerators, but it's a simple idea that you have tubes that a particle will travel down. They get longer and longer as the particle gets faster and faster. What is it that accelerates a particle in these tubes? Well, it's usually an electric field, and it's the fact that we have a positive plate and a negative plate, and depending on the charge of the particle, it will accelerate either one way or the other. So if you make this positive, a positive particle will go this way, and then you quickly switch over the field so that we can make sure that it continues travelling until it gets to this point, at which point you can switch the field back on so it's positive and it keeps on going. You obviously don't want it to be repelled by a positive plate here, so at some point you switch over the field so you can keep on accelerating it that way. So, you know, as the particle moves down the tube or moves down the accelerator, it gets faster. In order to have the same frequency of current, the tubes must get longer, so the particle spends the same time in each. Okay, quite a long answer. You actually wouldn't need to write all of this for the mark scheme. You could just literally write, you know, so that it spends the same time in each. But as this is not an AQA question, I thought I'd explain it a bit more fully. Okay, we've got a D0 meson, so that means it's a neutral meson, and you know, this is not an AQA question, but AQA are perfectly entitled to ask you about this because everything in the question allows you to answer the question even if you've never seen a D0 meson before. So it's D0, so that means it's neutral, and it decays into a positively charged cation and a negatively charged pion. So where is that going to occur? Well, it must be this point here, right? Why? Because firstly, it decays into two other particles, and clearly if it was this point here, that decays into three particles. And then secondly, and this is the heart of it for AQA because it's not really on the syllabus, but this is a cloud chamber photo, or probably a cloud chamber photo, and they only detect charged particles. So the D0 is neutral, so it doesn't show up in the image. Okay, it's only charged particles that are able to ionize the vapor and therefore cause these tracks in these types of image. Write an equation for this decay event. That's really easy. D0, and it tells you it goes into a positively charged cation, so a cation is a K with a plus positively, and a negatively charged pion. Okay, so 2 marks for that. Really easy. 3 conservation laws. So firstly, we've got charge. Now, let's write the equation up here just so we remind ourselves. So we've got 0 goes to 1 plus minus 1, so 0 equals 0, so charge is conserved. Momentum is always conserved, so the momentum of the D0 equals the momentum of both products added together. And you can see that quite nicely in this picture. The D0 is obviously moving this way, and then we obviously retain the motion in this direction, or the momentum in this direction, but we've also got some momentum in that direction which is cancelled out by the other particle moving in the opposite direction. And then finally, what have we got? We've got mass energy, or just energy. So the total mass energy remains the same before and after the decay. Now you could maybe talk about strangeness. You could also maybe say the strangeness of this is 0 and it goes to a strangeness of 0 and 0 as well, and that's probably okay, because that is obviously true. It's a decay, and we know that strangeness should be conserved in decays. Okay, CI, circle the correct combination of quarks in the list below which corresponds to the D0 meson. So it's not something you have to memorize, the D0 meson, but you can work it out. So firstly, it's a meson, so it cannot be 3 quarks because they're baryons. So which ones of these can it be? Well, it must be neutral. So let's look at C anti-U. So C is 2/3, and then an anti-U is minus 2/3. So that neutral is almost certainly that one. Let's just double check just to make sure we're not making a silly mistake. A charm is plus 2/3, and an anti-strange would be plus 1/3. So this would have a charge of plus 1. So definitely not this one. Suggest a possible quark combination of the positively charged kaon. So we need something that has a positive charge. So up, anti-down is the most obvious one, and that is something that you are expected to remember for AQA.